Hey there, welcome back to Short Text 331. Today we're going to continue our discussion of our very special matrix. So this is part 2 of our discussion of the discrete Fourier transform. And we defined our very special matrix as, in terms of the elements, jk of this matrix F, and that's given by 1 over square root of n, e to the I, 2 pi over n, j times k. And here n is, of course, the size of the matrix, which will be n by n, and j and k take values between 1 and n. We could have chosen j and k to be between 0 and n minus 1, and this formula would work just fine. And in fact, any interval on the integer line that's of size n will actually work. We can write that very simply as powers of a quantity w, where w is e to the I 2 pi over n. And we will refer to this F sometimes as the matrix of the discrete Fourier transform, or the DFT matrix, or the discrete Fourier transform matrix. So I mentioned that this was unitary last time in part 1, but I didn't really show it. So let's take a look at how to show that these elements indeed give you a unitary matrix. So let's see. So then we really have to show that f dagger f is 1, or f dagger is 1. And so let's see what f dagger is. So f dagger element KL is going to be f star element LK. And so we write that down, and that's 1 over square root n e to the minus I 2 pi over n k times L. So this k times L, of course, is the same as L times k. So KL, LK doesn't really matter, but this minus sign is crucial, and that just comes from the fact that complex conjugating e to the I, some real number, is e to the minus I, the same real number. And so with that in hand, we'll go ahead and contract indices as needed, and that means that we're going to take fjk as defined here, and we're going to take f dagger kl, and you can see that I chose the indices appropriately, so I could contract the second index of f with the first index of k, the first index k of f dagger, and so we got fjk, f dagger kl, and sum over k. And by the way, if I never use this word contraction, that's what it means. It means I take indices and sum over them. And so in this case, we sum over this index k, which is the second index of f and the first index of f dagger. And that's how you do matrix multiplication. You contract the internal indices, and you leave the external indices untouched. So j and l are untouched. And so let's see what happens from here. So I get 1 over square root of n in both cases, so that's a 1 over n. I have a sum over k, and then e to the I 2 pi jk from here, and minus KL from the other factor. Simplifying a little bit, I can pull out this common factor of K and leave this J minus L over here. And now we can evaluate and see what happens. So if J is equal to L, then this quantity is 1, because this exponent is 0, and so this is 1. And so I get to sum 1, n times divided by n, so that's 1. So for J equal to L, we get 1. So far, so good. Now, if J is different from L, it's a little bit more complicated, but let's see how we can do this. So if J is different from L, then this quantity is definitely not just 1, and this is not just 0. And so we're going to be summing from k equals 1 to n some quantities to the power k. And so what I did here is simply recognize that this quantity is some number to the power k. And that number I call alpha, and it's given here by e to the I 2 pi over n j minus L, wherever j and L are. And of course, here j and L are assumed to be integers. We can assume that they are between 1 and n, as mentioned here, both of them, and that would be enough for our proof. Either case, we get 1 over n up front, and then 1 minus alpha to the power n plus 1 divided by 1 minus alpha minus 1. Where did I get this from? This is simply the geometric sum. So find a geometric sum starting from 0 to n will give you this first factor, 1 minus alpha to the n plus 1 divided by 1 minus alpha. But we started the sum at 1, and so we have to subtract that term that we didn't really include. So that's the minus 1. That's where the minus 1 comes from. By the way, if you don't remember what goes up here on the exponent when you sum a geometric series, it's often the case that we sort of remember the formula, we don't remember the exponent. At least that happens to me sometimes. And then until I realized there's a very simple rule. First of all, the bottom is always 1 minus alpha, and there's nothing to it. But if the bottom is 1 minus alpha, then this has to be n plus 1 if the sum is up to n, because you see this, it's going to be always a polynomial of degree n. If the sum is up to n, then the polynomial is of degree n. in alpha. And so the only way this whole thing can be a polynomial of degree n is if the exponent up here is n plus 1, because down here we have 1 minus alpha dividing. Okay, so that's one way to think about it. At least it works for me. This may be too complicated for other people to remember, but that's how I think about it. And again, always remember that if the sum starts at 1 and not at 0, then you have to subtract 1, which is a contribution that you would have if you had the term for k equal to 0. Now, if we simplify this expression, we notice that we get this result. So 1 minus alpha to n plus 1 divided by 1 minus alpha minus 1. I go ahead and perform this sum, and so I get to add alpha and subtract 1 from this 1 here, and so the 1 goes away with this 1, and I get minus alpha n plus 1 plus alpha, the whole thing divided by 1 minus alpha, and I get to pull out alpha as a common factor, and so I get 1 minus alpha to the n divided by 1 minus alpha. And this is the crucial part that we have to look at. Why? Because it turns out that alpha to the n is, as you can see from here, is e to the I 2 pi j minus l. And no matter what j and l are, as long as they're integers, this e to the I 2 pi times any integer is going to be 1. And so this means that this alpha to the n is 1, and it cancels with this other one, and so this is 0. Okay, so we have managed to prove then that this asterisk that I put up here is going to be 0. So as long as j is different from l, we can play this game and do this calculation. There's no problem with it at all. And as long as j and l are integers, then we can guarantee that this result, or rather this alpha to the n, is going to be 1, and this 1 is going to cancel here, and this asterisk is going to be 0. And so we obtain then the result that if j is equal to l, we get 1. If j is different from l, we get 0, and that's the delta. That's the Kronecker delta. And in other words, we managed to show that f dagger is just 1. It's the identity matrix. And in the same way, by using exactly the same tricks and following the same structure of steps, you can show that f dagger f is 1 as well. And so f is unitary. That is, we have proven then that our matrix f, defined in this way, given the matrix elements shown here, then is a unitary matrix. And so our discrete Fourier transform is indeed simply a unitary matrix. Now, how is f a discrete Fourier transform? What does this really mean? We can use the name, but what does it mean? If you've ever seen a Fourier transform, it may not be obvious how that is a Fourier transform as a matrix. And so this is a bit of information about how you can think about that. So suppose you have V, a vector, in our n-dimensional space, and so you can apply the matrix f to that vector v, and you would obtain this result. So f applied to v, element k, is a sum from j equals 1 to n of 1 over square root of n times this factor times that comes from the element kj of the matrix, and then the vector element j. Now, this vector v may encode in its entries the n-point discretization of a function. So imagine you draw a function on a lattice. And this is very important because this is sort of what you would have on a computer. If you try to represent a function on a computer, you don't have a continuous function. What you have is a function evaluated at a discrete set of points, because that's how memory exists on a computer, on a discrete set of points. And so let's label those points 1, 2, 3, 4, and so on, up to n, and n could be anything, right? N could be 10 points, could be 100 points, could be 10,000 points. It doesn't have to be a multiple of 10. It could be 128 points, could be 7 points. But you have a discrete number of them, and so we evaluate our function at those at some points that we have chosen, and we label those 1, 2, 3, 4, and so on. Those are whatever points we decide, and then that's then our function evaluated at those points, and we store those in our vector, and we can call those just f sub j to abbreviate our notation a little bit. So f sub j simply means we took the function f and we evaluated that function at point x sub j, where j is a label that goes from 1 to n. And so if we do that, then we can relabel or rename some of the objects in this formula, which is applying f to our vector v. And so we obtain f tilde sub k, the result, which we have here, the result of applying f to v. We're going to call it f tilde elements of k. So it's going to be a vector with k going from 1 to n. And the result is 1 over square root of n, sum from j equals 1 to n of our exponent, we haven't changed that at all, times our function elements of j. And so what you have here then is something that really looks like a discrete version of a Fourier transform. So normally a Fourier transform will be an integral, And when you do that integral, you do an integral over an exponent that looks like this, divided by 2 pi or square root of 2 pi or whichever normalization you choose. And then your function evaluated at x, and the integral is over x, and you obtain a function of k. Well, this is the analog of that on a discretized lattice, on a discretized real line that takes n points. And so this is what you normally do on a computer when you're trying to do a Fourier transform. You do a discrete Fourier transform, and this is what's calculated. Now, I want to be careful about what's really calculated on a computer, because when you used one of the canned algorithms like FFTW or other stuff, usually this normalization is not included. And the reason for that is that different people prefer different normalizations. And so most algorithms prefer just not to use any normalization at all, which I guess is a choice of normalization if you want. But they do the sum. They do the sum very efficiently for you. And then you have to account for this yourself. Now, regardless of the normalization, no matter what your choice, then naively, doing this operation requires n squared operations, n squared sum and additions. So why is that? This operation itself, for fixed k, will take n operations, right? So n multiplications and then summing everything, and so that's order n stuff. But you have to do it n times, because k goes from 1 to n. And so that's where you get the n squared from naively. Now, it turns out that you can use the fast Fourier transform algorithm, which we haven't discussed, but which I mentioned last time. And that's one of the major, most important tools in signal analysis, the fact that this is possible to do and to do fast. And if you do that, if you use this fast Fourier transform algorithm in whatever version you may have access to, then you will be able to carry out this order n squared operations in order n log n. And the reason for that is not that the sum is done particularly fast, is that it turns out, as we will see in a future video, that you can avoid doing this n times. It's possible to avoid doing this n times. So you will effectively be doing a sum, but effectively every time you calculate the elements of this sum, you're going to get something for free. And when you accumulate all that stuff that you get for free, all those savings, then you get to reduce one of the n's to a log n, and so you end up with order n log n. So that's how the Fourier transform is often explained, as the ability to go from n squared to order n log n when transforming a function. This is the most common application, not the one we saw in the previous video where we transformed an operator, basically. So in the previous video, we saw a transformation of a matrix. This is how I explained it, as sandwiching a matrix between two Fourier transform. In fact, this is a Fourier transform, this is an anti-Fourier transform, and this is how you would transform a matrix and obtaining a diagonal matrix. And that kind of operation would take you from n cubed to n squared log n. One way to see that happens is that you can regard this operation, f dagger m, as a Fourier transform, or a discrete Fourier transform of n columns, so the columns of m. And so each of those would cost n log n if you use the FFT. And so then you have n squared log n total. This is very important for matrices M, as I mentioned in the previous video, that represent differential operators, because it's in many cases possible to go ahead and take a discrete Fourier transform and affect this transformation and obtain a diagonal matrix. And what that means, in short, is that in the same way that you can analyze a signal with a Fourier transform and obtain the spectrum, which could be very useful, and it could be a very simple thing to look at, even if the signal may appear complicated. So it's very beneficial, very convenient in many cases to then go ahead and take these differential operators, which may be complicated objects, and turn them into diagonal matrices. And a lot of the time what that implies is that if you have a complicated differential equation, as long as it's linear and has interesting specific properties like that, it's possible to sandwich that differential equation with Fourier transforms like this and turn it into an algebraic equation. And so you get a differential equation in one space and you transform to the other space with a Fourier transform, and you get an algebraic equation that you can solve right away. So that's, of course, a wonderful thing when you get to do that. And you get to do that a lot in physics and in many applications, as long as the equations that you're dealing with are linear. So that is getting a bit ahead of the game. We're going to have more videos on Fourier series and Fourier transforms and the various different flavors in which the Fourier series and the Fourier transform can be applied. in physical applications. But for now, that is all I have for you. I hope you enjoyed this video. If you like the content, please like and subscribe. If you're looking for a tutor in physics or math, in English or in Spanish, maybe I can help you. You can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below, and I'll see you next time.